Hello! I hope you're enjoying the book. I'm going to do some experiments now with the real radioactivity. First of all, let me introduce you to my Geiger counter. This is ex-Warsaw Pact military equipment. This is the probe for detecting radiation. It's got a headphone socket, but I've also connected an external microphone so that you can hear the clicks. Let me just turn it on. Now the clicks you hear, that's just background radiation, and that works out on average to about 15 clicks per minute, or 1 click every 4 seconds. Now that background radiation is coming out of the soil, from the rocks in the soil, and it's also coming down from space in the form of cosmic rays. Now it doesn't sound very much, but of course you have to accumulate that all the time. This is constant radiation that's hitting us all the time. So over a long period of time, it does add up to quite a significant amount. But for our purposes, we really want a bit more radiation than the background. So I got some uranium ore, and that's what we're going to have a look at now. Here is the uranium ore. You can see it's quite a dark grey metallic substance. It's actually called uraninite, and it's the ore from which you get uranium. It's also called pitch blende. In chapter 2 of my book, I told the story of how Marie and Pierre Curie had to process tons of this black pitch blende in order to produce a very small amount of radium. So there you can see the metallic uranium ore. Okay, so now we want to find out just how radioactive is the uranium ore. So let's bring the Geiger counter back in. As you can hear, it is quite highly radioactive. That's over 1,000 clicks per minute. And as I said earlier, background radiation is only 15 clicks per minute. Every click you hear represents the decay of a uranium nucleus. It's as if the nucleus is going pop, 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 pop. But even at this extraordinary rate of decay, there are so many atoms of uranium in this sample that even after 4.5 billion years, there will still be half the number of uranium atoms in there as there are at the moment. That's because the half-life of uranium is 4.5 billion years. It just shows how many atoms there are in the sample. Utterly extraordinary. And of course, if all of those nuclei decide to go pop at the same time, then you've got 4.5 billion years worth of pops all happening at the same time. You can imagine the amount of energy that's going to be released. And that is the principle behind nuclear explosives. Interestingly, the pattern of clicks, the click, 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 that is completely random. You are fundamentally prohibited from determining when a nucleus is going to decay. And that is because particle decay is governed by quantum mechanics. And quantum mechanics is fundamentally random. You can never predict when a nucleus is going to decay. It doesn't matter if you've got the most powerful microscope, the most advanced equipment. You cannot probe any deeper in order to determine when a nucleus is going to decay. So really, we're looking down at the very lowest level of reality here. That's what we're doing when we're listening to these clicks. And when we look down at that low level of reality, we find out that reality is completely random.